The Zeeman effect has much importance in the field of spectroscopy because it will proves or having very importance for explaining the fine structure of spectral lines and effect of magnetic field on the spectral lines. Okay, so let us see about the Zeeman effect. The Zeeman effect is a magneto-optical phenomenon in which the spectral lines are split up into several components when placed in a magnetic field. As the name tells, it is a magneto-optical phenomenon, means whenever a monochromatic light producing the line spectra is placed in an external magnetic field, then the single spectral line in the observation is found to be split up or got converted into number of several components. So there is a direct effect of magnetic field on the spectral lines, number of spectral lines. Okay, this effect of magnetic field on spectral lines was first of all discovered by Dutch physicist Peter Zeeman in 1896, and hence it is called Zeeman effect after his name. The Peter Zeeman has studied the effect of magnetic field, the effect of various strength of magnetic field on the spectral lines. Then he found that a single line is no more single, but it got converted into number of fine lines. So this effect of magnetic field on the spectral lines was known as Zeeman effect. There are basically two kinds of Zeeman effects. These two Zeeman effects are produced or formed depending upon the strength of external magnetic field and the nature of observation, means where the spectral lines are observed. Depending upon the direction of observation and the applied magnetic field to the spectral lines, the Zeeman effect basically has two types, two kinds. That is the normal Zeeman effect, and second one is the anomalous Zeeman effect. Normal Zeeman effect and the anomalous Zeeman effect. In the normal Zeeman effect, there is a splitting of spectral line into two or three components. Means a single spectral line is split up or got converted into two lines or three lines whenever it is placed in strong magnetic field. The field required for normal Zeeman effect is very strong. Okay, so effect of strong magnetic field on the splitting of spectral lines is called normal Zeeman effect. The components after splitting are symmetrically distributed about the original line. Means here original lines means a single spectral line which is produced by the source of light. So the after splitting of spectral lines, the components or extra components which are formed, they are symmetrically distributed on both the sides of a single line. Let us see in the diagram. Here the first figure where Zn is denotes is a and having wavelength of 4680 angstrom is a single spectral line of zinc in the absence of magnetic field. Then whenever this spectral line or the source of light containing single spectral line is placed in a very strong magnetic field, then a single line is found to be split up into three component lines. Here these two outer components are symmetrically distributed about the original line. Here central line is the original line. So Here we can say that a single line is split up into three components. One has the frequency same as that of the original line, and the upper component, that is this component, upper component has the frequency more than or wavelength more than that of the original line, and the lower component has frequency or energy less than that of the original line. So in this way, there is an effect of strong magnetic field on a single spectral line, which got split up into two components, sometimes into two components, sometimes into three component lines. So that is called a normal Zeeman effect. Okay, so it is about the normal Zeeman effect. Then the second one, the effect of comparatively weak magnetic field on the splitting of spectral lines is called anomalous Zeeman effect. Anomalous Zeeman effect. In anomalous Zeeman effect, there is a splitting of spectral line, or the single spectral line is found to be into more than three components when placed in an ordinary weak magnetic field, that is called anomalous Zeeman effect. Here, the splitting which is obtained in anomalous Zeeman effect is very complicated for observation. We cannot say exact what will be the or which are the exact components which are formed after splitting, because in this case a splitting is much complicated, as as we have seen that in a normal Zeeman effect, a single spectral line is found to be split up into two components or three components, and it is very simple to observe. So, due to the simplicity for observation and due to the simplicity in explanation, the normal Zeeman effect is called normal, not other reason is there, only there is a simplicity in observation, and it can be explained on the basis of simple classical theory. Therefore the normal Zeeman effect is called normal. The anomalous Zeeman effect is called so because it does not find its explanation on the basis of simple classical theory. For the explanation of anomalous Zeeman effect, we need to use the quantum mechanical theory. Okay, but among the two effects, the normal Zeeman effect is generally observed. But the anomalous Zeeman effect is generally observed, but the normal Zeeman effect is rare, because for its existence we require very strong magnetic field. Strong magnetic field is necessary, and hence it is rarely observed. Many times while performing the normal Zeeman effect, anomalous Zeeman effect, or the splitting corresponding to anomalous Zeeman effect is observed. Okay, but due to the simplicity in explanation, the normal Zeeman effect is called normal, and the anomalous Zeeman effect is not explained or cannot be explained on the basis of classical theory. Therefore, it is called anomalous. Okay. So these are the two kinds of Zeeman effect. Now let us see the experimental study of Zeeman effect. How these actual splitting of spectral line is observed. Okay. So for studying the Zeeman effect, initially we require a particular source of light, as a sodium vapor lamp or the mercury arc lamp. We know the sodium lamp has two spectral lines, D1 and D2 lines. Mercury arc lamp has four spectral lines. Whenever you use the zinc, then zinc has also a single line. The magnesium has four different spectral lines. But among the various spectral lines emitted by the source of light, we will focus on a single spectral line, and we will study the effect of external magnetic field on the single spectral line. Okay, now the for study purpose, the beam of light or the spectral line coming from the source is observed with the help of high resolving power spectroscope, because we have to focus on a single spectral line among the various available spectral lines. Okay, therefore we require very high resolving power spectroscope, and to analyze the nature of resultant spectral lines, whether the resultant spectral lines after observation or after its production, which kind of polarization is there. So to analyze the resultant light, we have to use the Nicol prism. So here Nicol prism is always connected to the resolving high resolving power spectroscope. So we can observe the lines. Also, we can get a kind of polarization that produced in a spectral lines. Okay. To observe, initially we will observe the normal Zeeman effect. So the normal Zeeman effect can be viewed or can be observed along or in two directions. First of all, in a longitudinal view, or the parallel to the a direction parallel to the direction of magnetic field, and the second of the direction is a transverse view. That means the observation in a direction perpendicular to the direction of magnetic field. So this observation is much simple, but to observe the emitted light parallel to the field or in a longitudinal view, the hole is drilled in the pole pieces of electromagnet. We have to drill one of the electromagnet or one of the pole piece of the electromagnet to observe the longitudinal view. Okay, now let us see the actual figure or actual experimental arrangement which is used for the Zeeman epoch, study of Zeeman epoch. So the first figure here, this figure indicates or gives the actual experimental arrangement. It consisting of a source of light. Uh, the light here, it is the source of light, the central part which is having a dumbbell shape, uh, gives the source of light is you're able to produce the line spectra, is placed in between pole pieces of electromagnet here N and S. These are the two pole pieces of a strong electromagnet. Okay, so these are the two pole pieces of electromagnet, and to observe the longitudinal view, the second, that is the S pole, is drilled. Here we can see the hole which is produced in the S pole, and here the spectroscope is placed for the observation of longitudinal view. Again, the spectroscope can be moved to observe the transverse view. Here the transverse view can be easily observed. Okay, so the magnetic field of very high strength is produced with the help of electromagnets. In a electromagnet, we can produce a magnetic field of desired amount by passing the high power current. Okay, so after the high magnetic field, a source of light is produced, a spectral line, and the single line is found to be split up into several components. Initially, when there is a no magnetic field, we get only a single spectral line, or single spectral line is found to be observed with the help of high resolving power spectroscope. In a longitudinal view, we can see here that the single line is found to be split up into two components, but the central component or the middle component or the component in place or in the position of original line is absent. In this case, means we can say that a single line is found to be split up into two component lines. In a transverse view, a single line is found to be split up into three component lines. Okay, so it is about the construction of the Zeeman effect. Now for the working purpose, now move towards the other slide. Here, the working or the experimental observation which are formed or obtained in a Zeeman effect. Here, after the producing the spectral lines by source of light as a sodium lamp or the mercury arc lamp, the single line is produced and a very strong magnetic field from the pole pieces of electromagnet is produced, and under the action of strong magnetic field the lines are split up into several components, and the observed lines are shown in the RHS of the figure. Here we can see the simple observations as in absence of magnetic field, a single line is observed at the center. Okay, so here it is a single line. It is a single line which is observed in when the external magnetic field is not present there. It is totally off. Again, when the spectral line or when the magnetic field is applied, then the single spectral line is observed to be split up into two component lines. So for this observation, as I have told you earlier, a hole is drilled in the one of the pole piece. Okay, then after observing the effect or the Zeeman effect along a longitudinal direction through the hole drilled in a pole piece, a single line is found to be split up into two component lines. Okay, we can see the second observational figure. These two component lines are symmetrically distributed about the central line, and here the central or the original line is absent in this case. Again, when the spectral lines are analyzed with the help of nickel prism, then it is found that the two outer components are symmetrically or they are circularly polarized along opposite direction. Means here inner component is circularly polarized in one direction and the outer component is circularly polarized on the other direction. That means both the component lines are circularly polarized. As we know, there are three kinds of polarization of light, that is the plane polarization, circular polarization, and the elliptical polarization. Here, the two component lines which are obtained in a longitudinal view, they are found to be circularly polarized along opposite direction, and the central component is observed absent in this case. Here, the central component is called a pi component. The name of this component is the pi component, and the outer components they are called the sigma components. Okay, means here we can say that the sigma components are present in this case and they are circularly polarized along opposite direction, and the pi component is absent. Okay, and this effect of splitting of the single line into two lines when observed along the direction of magnetic field is called longitudinal normal Zeeman effect. Okay, it is a normal Zeeman effect, but a normal Zeeman effect again classified into two kinds as a longitudinal normal Zeeman effect and transverse normal Zeeman effect. Okay, so in a longitudinal normal Zeeman effect, a single line is observed to be split up into two component lines which are circularly polarized along opposite directions. They are called sigma components, and a central line which is absent in this case is called pi component. Okay, again whenever we observe the effect of splitting along the transfer direction, let us move the this spectroscope along the transfer direction. In a transverse view, after application of the high magnetic field, very strong magnetic field, a single line is found to be split up into three component lines. Okay, the two lines are symmetrically distributed along the or around the central line. Again, a central line is present in this case which is at the position of original line. When the lines are analyzed with the help of nickel prism or by passing through the nickel prism, it is found that all the three lines are plane polarized. Okay, in this case, all the three spectral lines are plane polarized. The outer components, which are called sigma components, are plane polarized in a direction perpendicular to the direction of magnetic field, and a central component that is called the pi component is plane polarized in the direction of magnetic field. Okay, means here all the three components are plane polarized. Also, the pi component and sigma component, both these components are exist, and the outer components are plane polarized in a direction perpendicular to the direction of magnetic field, and the central component that is called pi component is plane polarized in a direction of magnetic field. Okay, so it is about the experimental observations which are produced or obtained in a normal Zeeman effect. So this effect is called transverse normal Zeeman effect. Means in a transverse normal Zeeman effect, a single line is split up into three component lines which are plane polarized. The outer components called the sigma components are plane polarized in a direction perpendicular to the direction of magnetic field. Here I have shown the sign of perpendicular. Okay, and the central component that is called the pi component is plane polarized in the direction of magnetic field or in a direction parallel to the magnetic field. It is about the transverse normal Zeeman effect. Again, when a ordinary weak magnetic field is applied to the instrument or to the spectral line, a single line is found to be split up into several components. So many spectral lines are observed or obtained when it is placed in an ordinary weak magnetic field. The lines have very weak strength, their number is very different, or in a or they are many in numbers, and its explanation cannot be given on the basis of simple classical theory. Okay, so it is about the construction working of the Zeeman effect. Now we can see here that the when the lines are split up into two components or three components, we can see here that the outer components are spaced or distributed around the central component having a wavelength difference of d lambda. Here d lambda is the wavelength difference between outer component from the center component. Here the lower component line has wavelength less than that of the central component by d lambda, and the outer component line or upper line has wavelength more than d lambda than the wavelength of original line. Here wavelength of the original line is a lambda, means wavelength of upper component will be lambda plus d lambda. Okay, lambda plus d lambda, and wavelength of the lower component is lambda minus d lambda. And this shifting of outer spectral line or outer components from the central component line is called Zeeman shift. It is called the Zeeman shift, and Zeeman shift plays an important role for many purposes. By simply by observing the or by noting the value of Zeeman shift, we can calculate or we can identify a nature of light. Also, we can see that how these lines are or how the Zeeman shift is affected, means which are the parameters or the physical quantities that will affect the Zeeman shift. Okay, so for that we have to see the expression for Zeeman shift. Okay, so I think only the 5 to 6 minutes are remaining. We can see the expression for Zeeman shift in the next lecture. 1 minute. 8 minutes are remaining only. Okay, we will continue. So for the expression of Zeeman shift, we always know the spectral lines are produced in a light due to the transition of electrons between or among the various energy levels. Okay, for that let us consider a electron of mass m that moving with a linear velocity v in the orbit of radius r in an atom. Okay, here electron is revolving around the nucleus in a particular orbit having radius r and having a linear velocity v. Okay, then for the circular motion we always know the for the circular motion the centripetal force is acted or is required. Centripetal force is required. Okay, the centripetal force acting on electron which is acted towards the direction towards the center of an atom is given by F equals to mv square upon r. Okay, here F equals to mv square upon r is the value of centripetal force. We know v equal to r omega, where omega is the angular velocity, r is the radius of orbit, and v will be the linear velocity. Put in place of v square, put the r omega square. The equation simplifies to the form F equals to m omega square r, where omega is the angular speed of electron or angular velocity of electrons. Okay, again it is that means the centripetal force is obtained before the application of external magnetic field. It is exist in an electron or in an atom due to the centripetal or due to the circular motion of electrons. Now let us see the effect of magnetic field, means what happens after the application of magnetic fields in an electron. So when an external magnetic field B is applied to the atom, then due to the influence of the magnetic field, the motion of electron is affected. Means we know if an electron moves in a clockwise direction, then the magnetic force acts in a downward direction or along the centripetal force. Again, we can say that hence the net force act on electron decreases. In the second case, if electron moves in anti-clockwise direction, magnetic force acts inwards. So in the first case outwards, actually their words is the outwards, and in second case the force acts inwards, and hence in this case the net force act on electron increases. So initially net force acting on electron decreases. In a second case, in anti-clockwise motion, the net force acting on electron increases, thereby the velocity of electrons either decreases or increases depending upon the value of magnetic force. Okay, therefore the change in total force on electron will be, in the first case the net force decreases, means resultant force acting on electron will be the centripetal force minus BeV, that is magnetic force. In the second case, the total force acting on electron is centripetal force plus BeV. So the change in force is equal to the magnetic force given by dF equals to plus or minus BeV. Put V equals to R omega. Therefore, the change in force acting on electron will be BeR omega plus minus BeR omega. That is our equation number 2. Now let us differentiate equation 1, which is F equals to mr omega square, that is our centripetal force. Here after differentiating dF equals to, here mr as it is, the variable quantity is only omega. The differentiation of omega square will be 2 omega d omega. Therefore, the equation becomes 2 omega mr d omega. That is equation number 3. Equation from equations 2 and 3, we can write 2 omega mr d omega equals to plus minus ber omega. The omega on both the sides also got cancelled. If we solve or this simplifies the equation for d omega, take 2 and m on other side, Also r from both the sides will be cancelled, omega cancel on both sides, r cancel on both sides. Therefore equation becomes d omega equals to plus minus b upon twice m. That is our equation number 4. Now we know the frequency of vibration, nu equals to omega upon twice pi. Okay, again differentiate this equation, d nu equals to d omega upon twice pi. Substitute in equation number 4. The equation changes from d omega into the d nu. Okay, so d nu equals to plus minus be in the numerator as it is, plus minus as it is. So in the numerator side put 2 pi and 2m, that is 4 pi m. So equation for d nu will be d nu equals to plus minus be upon 4 pi m. That is our equation number 5. Okay, now we have calculated the change in frequency. Again we know the relation between frequency and the wavelength of light and the frequency of a spectral line. Nu equals to c by lambda. Differentiate this equation, d nu equals to, here lambda is a variable quantity, nu is a variable quantity, only c is a constant, so c put as it is. Derivative of 1 by lambda, that is minus 1 upon lambda square into d lambda. So therefore d lambda equals to, we can send lambda square on this side, so the equation will be minus lambda square d nu upon c. Okay, so put the value of d nu from equation 5, and hence the equation simplifies to the form be lambda square upon 4 pi cm. That is our equation number 6. So equation 6 is the expression for Zeeman shift. We can see that the Zeeman shift is depends upon magnetic field or the strength of the magnetic field. Again it depends upon charge of electron, wavelength of the spectral line used, and the mass of electron, velocity of light, and so on. Okay, so by increasing the magnetic field we can produce more Zeeman shift. Okay, so it is about the expression for the Zeeman shift. So here all today's topic is completed. Okay, thank you.